Have you ever stopped to think about how engineers make decisions when there's just no single right answer? You know, how they have to balance things that seem to be complete opposites, like comfort versus performance or speed versus efficiency? Well, today, we're going to pull back the curtain on the engineering magic that turns these impossible-sounding trade-offs into a solvable math problem. It's called optimal control, and believe me, it's the secret sauce behind some of the smartest technology you interact with every single day. Okay, so here's our game plan. We are going to start with a classic dilemma from car design, and then we'll see how engineers use pure math to literally score performance. After that, we'll uncover the secret recipe for optimal control, see how it's tuned in the real world, and finally, we'll talk about why this whole idea is so much bigger than just a smooth car ride. All right, let's dive right in with something we can all feel, literally, the way a car feels on the road. You know, designing the perfect suspension system, it's basically a masterclass in trying to manage trade-offs. So what's your pick? Do you want a car that just glides over bumps, like you're floating on a cloud? Or are you the type who wants a stiff, super responsive ride that lets you feel every little detail of the road for that razor-sharp handling? Well, for an engineer, that's the whole problem. Those two goals are basically pulling in opposite directions. And here is that challenge, laid out plain and simple. For that super comfortable ride on a bumpy road, you want a really soft suspension to soak up every single jolt. But for high-speed cornering, you need a stiff suspension to mash those tires into the pavement for maximum grip. You just can't have a suspension that is both as soft as possible and as stiff as possible at the very same time. The objectives are in total conflict. So, how do we solve this? Well, if we want a computer to figure out the best possible balance, first we have to teach it what good actually means. And the only language a computer really gets is, you guessed it, math. The way we do this is by defining our goals as things we want to make as small as possible. So for comfort, we want to minimize the car body's acceleration. That's the force that literally shakes you around in your seat. For handling, we want to minimize how much the tire lifts off the road. And of course, it'd be nice to be efficient, so we also want to minimize the energy that the suspension system is using. The brilliant solution is to roll all of these goals into one single equation. It's called a performance index, or more commonly, a cost function. You can think of it like a golf score for the entire system. The lower the number, the better it's doing across all of our goals at once. Now, okay, an equation like this can look a little scary, but the idea here is actually beautiful and simple. This J is our total cost. We're just adding up the squared values of the things we don't like. The shaking, the tire lift, the energy used, and those little row symbols, those are just our tuning knobs. They let us tell the system exactly how much each goal matters to us. We can literally say, hey, comfort is twice as important as handling, or efficiency is our #1 priority. So now that we have a way to score any strategy the car could possibly use, how in the world do we find the one single strategy that gets the absolute best score, the truly optimal one? Well, it turns out there's a remarkably elegant recipe for this. And what's so cool is that this type of problem has a standard issue recipe that works for tons of different systems, not just cars. This equation right here is the general form, kind of like a universal template. Here, x is just the state of our system, you know, things like its position and its velocity, and u is the control effort we're putting in. This whole setup is what engineers call the linear, quadratic, or LQ optimal control problem. Now, the absolute key to this recipe are these two matrices, Q and R. Think of them as the master control dials for the whole system. The Q matrix sets the penalty for bad performance, how much we hate things like shaking or losing grip. The R matrix sets the penalty for the effort itself. So a really big R value tells the system that using energy is expensive, and it better be as efficient as it possibly can. Okay, so after all that setup, defining what we want, setting our penalties, the math gives us this incredibly powerful and honestly intuitive solution. It's a strategy called state feedback control. And all that means is that the best thing to do at any given moment depends only on where the system is right now. And here it is. This is the beautiful final result. The optimal control action, U, is just the system's current state, X, multiplied by a special matrix of numbers that we call K. That's it. All that complicated setup boils down to one simple, powerful rule. Just look at where you are, and this formula tells you exactly what to do next. It's incredible. So where does this magic K matrix even come from? Well, it's calculated for us by a really powerful mathematical engine. For those of you who are curious, it's called the algebraic Riccati equation. We don't have to solve it by hand. We just feed this engine our system's physics, along with our Q and R tuning dials, and it spits out the one perfect K that guarantees the best possible score. All right, let's make this feel a little more real. We're going to look at a super simple system. Engineers call it a double integrator, but you can just think of it as a basic model for something's position and velocity. And we're going to see how just by changing that R dial, the cost of effort, we can completely transform how it behaves. We're going to run two main scenarios. First, we want the system to get to its goal as fast as humanly possible, and we just don't care how much energy it burns. So we'll set the cost of effort, R, really low. Then, for the second run, we want to be super efficient. So we're going to make R really high, making effort very expensive. So specifically, we're going to test three different prices for effort. A low price of 0.1, a medium price of 1, and a high price of 10. Let's see what happens. Wow, okay, the results are fantastic. Check this out. When the cost of effort, R, is super low, the system responds incredibly fast. But look at that, it uses a massive, aggressive spike of control force to get it done. Now, when we crank R way up, making effort expensive, the response is much slower, much more gentle, but it gets the job done using just a tiny fraction of the energy. And that medium value, it gives us a nice, smooth balance right between the two extremes. And this right here is the key insight. As the designers, we get to precisely choose the perfect balance for whatever we need. We don't have to just pick fast or efficient. We can literally dial in the exact trade-off we want just by changing one number in our cost function. That is the real power of this whole approach. And you have to understand, this framework is so much bigger than just cars. This whole way of thinking, of defining a cost and then finding the one mathematically best way to minimize it, this is a cornerstone of modern robotics, of aerospace engineering, of economics, you name it. So let's do a super quick recap of the big ideas. Optimal control is what lets us turn these messy, complex trade-offs into a clean, solvable math problem. We get to define what good performance even means by creating a cost function. Then we can tune the system's entire personality just by adjusting those Q and R weights. And the final solution is this elegant and seriously powerful control law that always knows the best move to make based on right now. And that kind of leaves us with one final thought. This entire framework is about making the best possible decision when you're faced with competing goals. So just think about the complex trade-offs in your own world for a second, whether it's at your job, in your finances, or even in your personal projects. What problem could you solve if you could just sit down and mathematically define what the perfect score would be?